The collision of forces has been something that has been the core of many groundbreaking processes in science. Be it the collision of stars, celestial bodies, the collision of protons and neutrons, and much more. Whenever a collision has taken place between two massive forces, it has always resulted in a new force or body, and collisions will play yet a part in yet another process, and this time it's going to be between atomic particles. But in fact, it does have something to do with celestial bodies. Although these are celestial bodies which are known very little about, the celestial body in question is a black hole. If you like videos like these, then do leave a thumbs up and make sure to subscribe to our channel if you already haven't. The discovery of two black holes. These two supermassive black holes were found through decades of radio telescope observation data carried out by a team of Caltech astronomers who discovered this phenomenon from a radio pattern present in the deep. It was something that has never been observed before. About 9 billion light-years away, there are two massive black holes revolving around each other, and nothing good is expected from these two bodies of nothingness. However, their motion isn't expected to last forever. Around 10,000 years from now, the pair will collide with each other. Of course, we won't be present at that time, but as we said that whatever and whenever they do so, it won't be pretty. This is because once these two massive black holes collide together, they will combine into a single abyss with a strong enough force to disrupt the laws of time and space by the eruption of ripples. Each supermassive void is considered to be so enormous that our minds can barely comprehend its reach. Their mass is 1,000,000 times bigger than our sun, but they're pretty close together on a relative cosmic scale. The supermassive black holes are separated about 50 times the distance between Earth and Pluto off debatable planet. To put things into context, a black hole merely half the size of a golf ball would have a mass equal to our entire planet. Scary, no? Before these black holes were looked into, they were simply a flickering light point some 9 billion light-years away. The point waxed and waned in brightness every 5 years in a perfect sine wave like clockwork. But that isn't the feature of it that stood out. The thing that made this point of the light special was where the signal diverged from the pattern. Over nearly 50 years, the point of light has obeyed like a clockwork cycle of 5-year pulses, apart from the 20 years where it did not. 5 observatories made the confirmation of this light point: University of Michigan Radio Astronomy Observatory, MIT's Haystack Observatory, the National Radio Astronomy Observatory, NRAO, Metahovi Radio Observatory in Finland, and NASA's Wide Field Infrared Survey Explorer, or WISE, space satellite. After confirmation was received from these observatories, it was clear that there was no error. Pooling data managed to show us that the oscillation of light formed a clear and distinct pattern which managed to keep the mystery hidden. At the center of this majestic sine wave is a big wobble, a dimming that lasted for merely 2 seconds. The fluctuation was an anomaly since it didn't match any particular astronomical phenomenon. So did the team behind this research develop a logical explanation for this? Let's hear from those involved. When we realized that the peaks and troughs of the light curve detected from recent times matched the peaks and troughs observed between 1975 and 1983, we knew something extraordinary was going on, said Sandra O'Neill, lead author of a new study describing the astronomers' observations. But its identity would come from a surprising direction, not astrophysics, but simple orbital dynamics. But let's see what happens when two black holes collide. We did mention that something terrible is likely to happen when they do, but what it is shall be looked into by us. Collision of two black holes. Galaxies usually have black holes at their centers. Our Milky Way, for example, has a supermassive black hole known as Sagittarius A, which is present at its core. When black holes have cleared their stellar environs, they become invisible and almost undetectable. Sometimes they put on a show known as a quasar. A quasar is an active core of a galaxy known by a supermassive black hole and illuminated by glowing hot material falling in from its accretion disk. Specific quasar release a jet of plasma or raw neutrons. When these jets of plasmas have their beams pointing straight at the Earth, they are called blazars. Several processes take place that causes blazars to change in brightness, but none of them is a match. When the co-author in the study, Roger Blandford, stepped in and offered a different idea, the explanation he offered was that instead of an internal phenomenon, it was orbital dynamics. The fluctuations made sense if the point of light wasn't a single entity but two galaxies that were about to collide with each other. One of them had a regular supermass black hole at its core. The other blazer, instead of being pointed dead on at us along with our line of sight, the blazer's jet was about 5 degrees off its axis. As the black hole and blazer whip around their gravitational center, which funnily enough is their common sight, the blazer begins to move in a circle, similar to a flashlight. Sometimes it is in our eyes more than that of other people. We knew this beautiful sine wave had to be telling us something important about the system, said project mentor Tony Reedhead. Roger's model showed us that it is simply the orbital motion that does this. Before Roger worked it out, nobody had figured out that a binary with a relativistic jet would have a light curve that looked like this. So the person that brought the turning point in this study was Mr. Blanford. The two supermassive black holes have met. What happens next? Forming waves. When two galaxies come together, the supermassive black holes present at their centers tend to sink towards the gravitational center of the new combined galaxy. As the black holes spiral towards one another, their enormous masses distribute space and time, which manages to kick up gravitational waves. Eventually, the black holes tend to collide with each other, and when they do, each of them contribute to their already colossal mass, which creates a newer and more gigantic black hole at the core of the new galaxy. If this blazer does have a companion of its own, then the next step is to try to detect the other supermassive black hole using gravitational waves. The National Science Foundation's LIGO, Laser Interferometer Gravitational Wave Observatory, which Caltech and MIT jointly operate, can detect gravitational waves created by colliding black holes of perhaps a few dozen solar masses. LIGO contributed immensely to the project when gravitational waves were detected the first time around. Still, LIGO cannot see this collision because the mass of these black holes is outrageously huge. These supermassive black holes at the centers of galaxies have millions to billions of times the mass of our Sun. These enormous collisions manage to give off lower frequencies of gravitational waves which LIGO cannot detect. However, the upcoming Laser Interferometer Space Antenna (LISA) mission will detect merging black holes present in a range of 1,000 to 10 million solar masses. The finding of the PKS 2131021's binary black hole system will aid us in studies of gravitational waves or ripples in the universe, which are formed by super strong gravitational forces, discussed first by Albert Einstein about a century ago. The existence of gravitational waves was considered unprovable as ripples are a consequence of general relativity, which bends time and space so that we haven't fully comprehended. However, LIGO doesn't deliver all the bad news. It provides Einstein's fascinating theory about spacetime, which tells us that spacetime is a fabric that can be disrupted by gravity the same way dropping a coin in a lake would send ripples across the water. LIGO continues to assist in studying the warping of spacetime, and study authors emphasize its detector, which can't match ripples caused by supermassive black holes like the two found in PKS 2131021. LIGO tops out at finding waves produced by voids that only have a mass that is about a dozen times the mass of our Sun. This is why scientists need to detect sinusoidal light wave patterns, which are explicitly created by black hole jets for black holes, which are more significant, and this is why LISA is being developed. This work shows the value of doing accurate monitoring of these sources over many years of performing discovery science. Blanford said in a statement, "These two supermassive black holes seem like bad news right now, and when they do collide, it'll be bad news. But as we study their nature and complexity, we eventually realize how insignificant we are in this universe." That's all we had for this video. If you like this video, then do subscribe to the channel, make sure to give this video a thumbs up, and we'll see you again in another video very soon.